Alright, so this is going to be a quick video, but here you have a pink square and the yellow circumcircle, and the claim is that if you see the red point, which is any point in the plane, and you extend lines from the vertices of the square to that point, then those lines will cut the circumcircle at points which form the blue quadrilateral, which form a harmonic quadrilateral. So harmonic quadrilateral just means that the pairs of opposite sides of the blue quadrilateral have equal products. So basically, this length times this length equals this length times this length. And so just a quick proof of that, which involves the law of cosines and some basic geometry. So here I've just written down a diagram. So imagine that in the center of this is your point P, and imagine that the D1, D2, D3, D4, imagine those are the distances from P to the vertices of the square. Okay, so, and also just for reference sake, let's just call the angles that P makes with the different lines going to the vertices. Let's just call the top angle A, the side angle B, the bottom angle C, and the left side angle D. So squares are obviously harmonic quadrilaterals. That's pretty obvious. So from that we can deduce from the law of cosines. So this first term right here, d1 squared plus d4 squared minus 2d1 d4 cosine d, that's going to correspond to that's just the square of the left side of the square. So that's just the square of the left side of the square. And then similarly this one, d2 d3 d2 squared plus d3 squared, etc. This one is going to be the right side of the square squared. And then similarly, this one is going to be the top side of the square squared, and this one is going to be the bottom side of the square squared. I know this figure is not drawn to scale, and I know that these points that d1, d2, d3, d4, and I know that those vertices of those lengths do not form a square, but I'm just drawing it for reference sake. So this equation is obviously true. And then what I did here is I divide the whole equation by d1 squared, d2 squared, d3 squared, d4 squared. So that's what I did here. I divide the whole equation by d1 squared, d2 squared, d3 squared, d4 squared. And then when I do that, oh yeah, and also another thing that I did is I multiplied by c to the fourth. So I guess just for extra clarity. And what is c? C is going to be essentially the power of the point of point P. And for those of you who are familiar with geometry, who might not be familiar with the power of a point theorem, it just means that if I have any point P and I have a circle of radius r, and let's say P is d distance away from the center of the circle, then if I draw any chord from P that intersects at B and D, then if PB equals D1, then by the power of a point theorem, PD is going to be equal to C over D1, where C is R plus D times R minus D. So that's just what this C is the same as this C over here. So yeah, what I did was from this original big long law of cosines equation, I divide the whole thing by d1 squared, d2 squared, d3 squared, d4 squared, and then I also multiply the whole equation by c to the fourth, or which equivalently is saying I multiply this thing by c squared, and this thing by c squared, and this thing by c squared, and this thing by c squared. So I can just say I multiplied this one by c squared, c squared, c squared, c squared. Yeah, so when I do that, I get exactly, you see this is exactly c squared over d4 squared plus, yeah, so I get these terms. So this one becomes this one becomes this term becomes this, and then this term becomes this. So what you hear is, let's just look at the first term. So this product, or this factor, you notice is exactly the square of this long blue length, because you notice d1 and d4, if I extend length d1 and d4, if I extend it to cut the circumcircle again, then I will create this right blue length. And so by the law of cosines and by the power of the point, if I, like for example, if I extend d1 to cut the circumcircle again, then the rest of the chord that cuts the circumcircle, like imagine if I extend d1 through point P, then that chord will meet the circle again and at some other point, and the distance from P to that other point is going to be c over d1. And similarly for d4, if I extended d4 through point P to cut the circumcircle at another point, then P to that other point is going to have a distance of c over d4. And so those two invisible lengths that are not drawn, those two invisible missing lengths will be the sides of a triangle that contain this right blue side. And then by the law of cosines, since those missing lengths are c over d1 and c over d4 respectively, by the law of cosines, this first product is exactly going to be the right blue side squared. And similarly, this one is going to be, so this one involves d2 and d3, so this second factor is going to be the left side of the left blue side squared. And then on the other side of the equation, d1, d2, this third factor is going to be the top blue side squared. And then the last factor is going to be, you can see we have, or actually no, I misspoke. d1, d2, if you extend a d1, d2, they will actually meet at the bottom. So this third factor will be the bottom side squared. And then the fourth factor, if you extend d4 and d3, will be the top side squared. So you can see this equation exactly says that the, so this one is the right blue side squared times the left blue side squared equals the bottom blue side squared times the top blue side squared. And then we have, so therefore we're done.